previously I have derived the formulas for marginalization and conditioning for multivariate Gaussians in the moment form. So now I want to also derive similar formulas for multivariate Gaussian in canonical form. So I make a claim that if my PDF of x and y is given as a canonical Gaussian, n minus 1, x and y, and then potential vector, I call it vector A and vector B, and information matrix, joint information matrix, lambda xx, lambda xy, lambda yx, which is the same as lambda xy transpose, lambda yy. So if it's the joint distribution of x and y is given like this, then it's the marginal first, and the marginal can be written as canonical Gaussian in y with the potential vector, which I call vector m, and information matrix, which I call lambda m, where these then are vector m is vector b minus lambda xy transpose lambda xx inverse vector A, and then the information matrix lambda m should be lambda yy lambda xy transpose xx inverse lambda xy. So that's the first claim, that this is going to be the marginal distribution of y. And then at the same time I also look at the conditional distribution of x given y. So my claim is that this is a canonical Gaussian in x with somewhat simpler form, A minus lambda x y is y as a new potential vector. Then it's going to have an information matrix, which is lambda x x. Okay, so those are my claims, and then I'm going to prove those claims. So I'm going to start with the marginalization, because I'm planning to use that later on for the conditioning. Now, before I embark on this, there's a lot of matrix inversion involved here, so I would like to have some results for inverting matrices handy. So I have a general rule. This is in the book. I think this is currently N6 in appendix. You don't have to read appendix from end to end, but you should be aware of what is in the appendix, and these matrix inversion rules are extremely important. So let's say I have a matrix looking like this. So 4 blocks in that matrix, and I want to invert it. Of course, if this was only numbers, we know how to invert this from mathematics 3 or even earlier. But you have a block matrix, so it's a bit more complicated, but I have rules for this. So this is going to be something that looks like this, starting with the lower left part. Minus D, C, A inverse B. Everything inverse, C and A inverse, okay? Then the lower right part is going to be D minus C, A inverse, B, the whole thing inverse. And then I don't really care about the upper parts for reasons that you will see very soon. So this is a general result that I'm now going to use. So first I'm looking for this thing called lambda m, that's the marginal information matrix. So this is the same as P or Y, the covariance matrix of Y inverted. what is that again? Where PYY is the same as the zero and identity matrix times the joint covariance. And then again I have to multiply with the zero one matrix afterwards. So if I do this matrix product here, I'm going to get PYY, and then the whole thing is inverted. So, and then I replace this with the inverse of the information matrix, and I get information matrix instead, and xy, lambda xy transpose, lambda y. I'm going to invert that whole thing because then it becomes the covariance matrix. And then I have 0 and I, and the whole thing inverted. So then I want to next time spell out what to get here. I don't need to care about all the blocks because this 0 I thing is going to make sure that it's only this part when I invert it, the lower right part that matters. So I get then I don't care about lower left, I don't care about upper left. Lower right is lambda y minus lambda x y transpose, lambda x inverse, lambda x y, the whole thing. Again, upper right, I don't care about either. Invert the whole thing. And then I end up eventually just inverting this thing here, so I get simply lambda y minus lambda xy, lambda x inverse, lambda xy. Okay, so then I got the covariance of the marginal. Now already at this stage you can notice that how this becomes more complicated than marginalization in moment form, because in the moment form marginalization is just cutting away everything but this thing. But now you see I end up having to invert something, and there are some cross information, let's call it that also appears in this formula. But I'm going to move on to the potential vector for the marginal. So the potential, to start with find the potential vector, and I can start with I have a moment form. So the expectation of y, the marginal expectation of y, which I call b in the proof with moment form. So what is this? Well, this is the same as 0 and I thing times the full expectation of the joint, which is the information matrix times the inverse times the potential vector. So here I have an information matrix. Going to invert, and then I have the joint potential vector, vector A and vector B. So 0 and 1, and then again I don't really care about all the elements in the inverse inverted information matrix. Now this I is going to make sure that the first row is, the 0 here is going to make sure that this first row is unimportant, but the I means that the lower row is important, and then again, this again is going to be multiplied both eta A and eta B. So this means now that I need the lower left, which becomes, now if you look at this general result, this first part here, that is lambda m, that's the same as the marginal information matrix. So I just put that there instead of spelling it all out. I'm going to have this thing, lambda xy lambda x inverse. And then this top is just the marginal information matrix, lambda m inverse. And then I add some question marks. I don't care about the upper parts. A and eta e. So, what is then eta m? Well, that is eta m is equal to the information matrix times the corresponding expectation. So lambda m, and then I have this expectation, which is what I get when I multiply all this together. So then I get lambda m inverse times eta e minus lambda m inverse lambda x y transpose lambda x inverse and lambda a, which is the same. When I cancel the lambda m's, I get eta b minus lambda x y transpose lambda x inverse eta a. So then I have the marginal distribution of y. The next step is to find the conditional of x given given y. That should hopefully not be too difficult, because you see the expression for the conditional is something much simpler. So the conditional of x given y is the same as the joint divided by the distribution of y. This is going to be, well, it has to be proportional to some exponential in a quadratic form. So let us take a look at how that looks. And then I can simply start with what I have up here and use the standard formula for the canonical form and just multiply things together. So first I have the first order terms for the potential vectors. So x and y multiply together with their respective potential vectors. Then I have the second order term, which is x and y multiplied with the information matrix, no potential vectors involved now. That's how canonical form works. So I have x transpose lambda x plus x transpose lambda x y plus y transpose lambda x y transpose x plus y transpose lambda y. So no inverses, no potential vectors. This is canonical form. Then I need to subtract then the terms from this p of y. So I just continue in a new line, still within the exponential. Eta e minus lambda x y transpose lambda x inverse eta a, and this is the potential vector, so the whole thing transpose times y minus 1/2 y transpose lambda y minus lambda x y transpose lambda x inverse lambda x y. So now all the ugly stuff comes because our expression for the marginal was quite ugly. But there is a lot of stuff that we can ignore here. rid of. Because what I'm looking for now is I'm looking for a density of x. I'm not looking for a density of y. So if I just have all the quadratic form that describes the behavior of x, I'm done. Now that means that terms like all of these pure y terms I can actually just forget about. But I'm left with this. So in a sense, actually, writing down all of this is kind of redundant. I do it to show there what P of y is, but I don't need to care about it. It carries no information about x. Yeah, this is what I have, and this is the same. Just write it slightly different. Exponential of x transpose times f of a minus lambda x y plus 1/2 x transpose lambda x. So this is the same as constant sense lambda x given y, and this is my potential vector of x given y. And then I have proven those rules for marginalization and conditioning in canonical form.